I'm standing in the San Andreas Fault Zone just north of the Pinnacles National Park. It cuts through the Coast Ranges here into the Cienega Valley, wine country near Hollister, California. Our understanding of the geology of the Coast Ranges of California and other parts of the planet owes a debt of gratitude to the people who developed the Tectonic Model. Today we're going to look at that development of the model, a model that wasn't sought for, but was discovered as people moved to understand planet Earth. First, we need to talk about the elephant in the room. No, not that elephant. This one. There's an old child's story about the blind villagers who ask their neighbors to lead them out into the forest to encounter the elephant. Once there, each of them went to a different part of the elephant and touching it, feeling it, discovering it for the first time, argued amongst themselves on the nature of the elephant. Some vehemently argued that an elephant was like a great stone wall, while others, grabbing the tusk, argued that it was like a spear, while still others grabbed the trunk and insisted that it was like a snake. You see, prior to the advent of the Tectonic Model, geoscientists on the planet thought of the Earth in very different ways. Volcanologists looked at volcanism in the Earth and didn't understand its relationship to earthquakes or mountain buildings, while paleontologists thought of the Earth in a very, very different way. And it wasn't until plate tectonics came along that they started to understand the Earth as part of a larger system. And by doing that, start to understand the part of the system they were studying within the context of the larger whole. Now, how that model that's so important and critical to the earth sciences today came about isn't how most people would think. You would think that this was the effort of a collection of scientists to discover what was truly happening on the Earth. And that's not it at all. The scientific model that we refer to as plate tectonics was bumbled into through a series of discovery. And science at its heart is still about discovery. Because what came from those series of seemingly unconnected discoveries was a model that explained everything about how the Earth works. It was nothing short of a scientific revolution in the earth sciences. And if we had to trace it back, it would go back 100 years and start with a question about ice. And a man named Alfred Wegner. Alfred Wegner was not a geologist or a solid earth geoscientist at all. Al Wegner was a meteorologist and physicist, best known for his study of polar atmospheric sciences. In fact, he wrote all of the important early papers on the subject. But that isn't what he's best known for. He's best known for a crazy idea about moving continents, something that he never referred to as continental drift, but was later labeled that, is attributed to his work, his findings. See, Al Wegner was a little ahead of his time in many ways. You're looking at the Greenland ice sheet. The Greenland ice sheet is about 2 miles thick and sits over Greenland, and it's the remnants of the great ice sheet from the last ice age over the northern hemisphere. Al Wegner was interested in the ice age. He was interested in how climate change actually worked. And Al decided he was going to go to the polar regions and work with glaciologists, and while doing his studies on atmospheric science, he was going to look over their shoulder and see what they did. Now, in modern studies of glaciers, we'll put teams in the field who study the nature and flow of the ice sheet, but Wegner was interested in something more. Al Wegner was really interested in getting into the nitty-gritty and understanding how you could look at the ice in terms of what had happened in the past. And in that quest to understand things, Al Wegner is reading all he can about glaciation and about using glacial deposits and the features glacial ice eroding the surface of the earth will leave behind that leave a record of their existence. And in the midst of doing that, trying to study the major ice ages of the northern hemisphere that happened relatively recently in geologic time, he stumbled across something. He found in the literature from the southern hemisphere, South African geologists, Australian geologists, South American geologists had all written about glacial deposits that were more than 200 million years old that existed in the southern hemisphere. Now, you just don't find them in the northern hemisphere, but Al Wegner was excited because he felt he had an opportunity to study a glaciation, a climatic event all on his own that happened more than 200 million years ago. And he decides he's going to go to the southern hemisphere and start studying this. He's going to ask geologists to lead him around and show him the geology relevant to this, and he's going to reconstruct the ice sheets and climatic change in the southern hemisphere. Well, what happens instead is he comes back and writes a book called On the Origins of the Continents and Ocean Basins. In that book, he's going to suggest, and actually is going to assert, that more than 200 million years ago, the continental land masses that we are familiar with today were all assembled into a single continental landmass that he referred to as Pangaea. And Pangaea was mostly in the southern hemisphere. Now, his lines of evidence for this, which were the direct result of his question about ice in the southern hemisphere, involve a few things, some that are rather obvious. The fit of the continental margins if you look across the Atlantic Ocean basin. Now, a lot of people point to that. Al Wegner was not the first one to point that out. In fact, there were kids' games where the Atlantic Ocean had been cut out and you could literally fit the various continental margins of Western Africa and Eastern South America and part of the east coast of North America back like puzzle pieces. Now, this is a line of evidence. If we look at how closely those match, what we'll see is they're a very good match. And considering the continental margins rather than the coastal lines themselves, an incredible match with a few areas of overlap, which is to be expected. After all, there was some 200 million years of geologic processes acting on those margins after the breakup of Pangaea. But it's the other lines of evidence that are most compelling. Now remember, he's going to the southern hemisphere and he's looking at the geology. Well, some of the things that didn't make sense until after he reassembles Pangaea are things like on the continents, the fossil distributions. For example, and here's one example, this is a fossil Mesosaurus. Very, very similar to modern crocodiles, although not directly related. They're estuarine creatures that had limited habitat. Now, the map you see here shows fossil distribution. And for years before this, paleontologists understood that a fossil distribution map really was a window into ancient habitat. And as you can see here, these estuarine creatures who were not capable of swimming in the open ocean are separated by 3,000 miles of open ocean. How in the world do you establish two distinct fossil habitats or two distinct habitats for a creature that really can't communicate with one another? That isn't something we see either in the fossil record or in modern times. That's very interesting. And this isn't the only example. Wegner also saw 12 species of Glossoptera. Glossoptera is a type of fern, fossil fern. Those fossil distributions also spanned ocean basins and made no sense until you reconstructed Pangaea. In fact, if you look at reconstructions of Pangaea, fossils that are more than 200 million years old we can see the fossil distributions start to merge, and you have a very, very easy to explain habitat for various species, both of plants and animals. Now, this is compelling all on its own, but it's within the context of the larger geology. The other thing that fits back together like puzzle pieces when you take out the Atlantic Ocean basin and do things like push the east coast of South America up against the west coast of Africa is that the geology matches up. We get rocks of similar age and type that are separated by thousands of miles of oceanic crust today, that when we reform the continent of Pangaea, they fit together like puzzle pieces. And it's not just the rock types themselves, it is other things like mountain ranges and structural belts within the rock. When you take Pangaea and reassemble it, what you get is an explanation for even ancient mountain belts. Here we're looking at a mountain belt system in North America. It's actually the mountain belts that form the suture of the original Pangaea. The mountain belt ages, styles of deformation, faults, and folds within the rock match up once you reassemble Pangaea. And you would think that this is really compelling evidence. And Al Wegner was making notes in his notebook as he was going from space to space to space in the southern hemisphere, learning from geologists and looking at the rocks. But remember, his question wasn't about moving continents or resolving paleontologic issues. It was about resolving an ancient ice age more than 200 million years old that happened in the southern hemisphere. And that's when he came across glacial deposits. Now, these are glacial deposits left over in the modern environment on the surface. The glacial deposits he was looking at were literally buried within the rock record itself. But glacial deposits are very, very distinctive. They're poorly sorted breccias. They're made with large boulders and fragments and dust and sand and everything in between. And they are deposited on top of a surface that has been eroded by glacial ice. The erosion by glacial ice leaves behind glacial polish and something called striations, and we're looking at that now. And you can almost think of this like a giant sandpaper block grinding across the crust of the earth, polishing it. But it's the grit of the sandpaper, which would be the sediment within the base of the glacier went over the rock. It's also gouging out pieces of the rock and scratching the surface. These are the striations. The glacial ice literally moves in the direction of those lines. And more importantly, one of the things that Al Wegner learned from his glaciologist friends when he was studying ice in the northern hemisphere is when you run your hand on those striations, if you run in the direction the ice is moving, it's very smooth. If you run your hand backwards in the direction the ice had come from, you get something we call the chatters. It's very, very rough. So given that the line has an orientation and you have a direction, you literally can put an arrow on your map. You can say the glacial ice was here and it moved in this direction. And from this, what Wegner could do is reconstruct that glaciation. And here's where things really got interesting for Al Wegner. His map doesn't work. See, what you're looking at is a map of the ancient glaciation. The glacial deposits here are shown with a blue tint on the continents. You can see arrows showing the direction that the ice was moving. This violates three different laws of the universe. The first two have to do with thermodynamics and thermal properties. Ice forms over the continents. Huge ice sheets will form up to 2 miles thick and can move out in shelves over the ocean, but ice won't collect on the ocean itself, not in any vast kind of thick ice sheet. The other problem that we have here is that if you look at the position of India north of the equator, this ice that was mostly over water would have had to cross the equatorial zone in this one location and not others. That's a second law violation. And then the third violation is the violation of the law of gravity. If you look at the arrows, it shows that ice was moving uphill off the ocean onto the continents in all directions. To reconcile these problems, Wegner looked at all the other geology and came to a startling conclusion. If you reassembled the land masses so that the geology, the paleontology, the fit of the continents all worked, then so did his glaciation. See, it wasn't a remnant of some ancient glacial period in the southern hemisphere similar to the ice ages of the northern hemisphere. Instead, it marked a time when there was much more land mass gathered around the south pole of the planet, increasing the polar ice cap. When Pangaea broke up and these various land masses moved to the north into lower latitudes, the heating up melted the ice and left behind the glacial deposits and distributed them over time to their current locations. Well, Wegner, realizing that this was a great discovery and find, and feeling he had overwhelming evidence, he writes a book. It's published in 1915 on the origin of continents and ocean basins. It wasn't a bestseller, but it was picked up and read by a number of people. Mostly, these people, scientists in the Northern Hemisphere, geologists, geophysicists in places like North America and Europe, hadn't seen the rocks that he described because much of his evidence came from the Southern Hemisphere. And you have to also understand that at the time, motions of the continental crust or the crust of the Earth were considered in vertical senses. You had normal faulting and the reverse of normal faulting with thousands of feet of vertical relief in mountain ranges and to account for the deep ocean basins. But the idea that the continents themselves had moved thousands of miles with respect to their current positions, well, that was preposterous to most of them. And it didn't help that somebody coined the term continental drift. Now, Wegner doesn't use that term. But once the term stuck, it had an additional problem. That additional problem is the idea that the continents are plowing through oceanic crust also was preposterous in the fact that continental crust is much less dense than the basaltic oceanic crust. It would be like butter moving through steel. And at the time of his death, and Al Wegner died in 1920s, he was on the polar ice sheet in Greenland. He was looking at polar atmospherics, and a storm came in, and he passed away. But at the time of his death, there weren't a lot of people who thought that his musings were anything more than that. Well, that's different today, because if you look today at a reconstruction of the planet using our best geology, geophysics, everything we know, and modern information systems, thousands of geologists putting all of that data in, we come up with a view of the past. This happens to be the late Permian, some 255 million years ago. Look familiar? Yes, this is a reconstruction of Pangaea at that time, 255 million years ago. You can see Gondwana, which is the southern part of it, sitting around Antarctica in the south. Now, at the time of his death, his book was out there, his evidence was out there, and it's kind of hard to understand how it wasn't accepted when you consider what it was. So let's look at the lines of evidence for Al Wegner's model. One is the fit of the continents, although, again, he wasn't the first to propose such a thing, the fit of the continents. And even school kids had games, puzzles, where you remove the Atlantic Ocean basin and fit the continental margins of Africa, South America, Europe, North America back like puzzle pieces. It is part of a larger list of evidence, like fossil evidence. Reconstructing Pangaea makes numerous fossil distributions that are more than 200 million years old make sense, especially in the southern hemisphere. This is also true for the geology itself. The geology itself doesn't make a lot of sense, more than 200 million year ago geology. But when you look at the rock types, the similarity in ages and the type of rocks across the ocean basin separated by thousands of miles of basaltic oceanic crust, structural similarities, these would be the deformational patterns in the rocks, right up to mountain ranges that formed during the continental collision that assembled Pangaea. This is pretty overwhelming evidence. And then finally, when you look at the paleoclimatic evidence, this is the distribution of the glacial till and the mapping of the movements of the ancient glaciation more than 200 million years ago. When you put these all back together, they fit together one way. They fit together with a massive supercontinent existing on the planet more than 200 million years ago. Now, after his death, Al Wegner didn't have a lot of people who were proponents of this model, and the world was busy with a couple of world wars, an economic crisis, a pandemic. You get the idea. But after the war, 1940s into the 1950s, science, which had developed a lot of technical new techniques and new technologies to support the war effort, well, that was being assumed back into science for things like studying the Earth. And one of the things that had been studied is the magnetic field of the Earth. That study of the magnetic field is going to go on to help people really understand that Wegner wasn't so crazy and that the continents had been moving around after all. If we think about the Earth as a magnetic field, one of the things you'll notice in middle school earth science textbooks is a picture something like this. It kind of portrays the Earth as having a bar magnet in it with a simple magnetic field with north and south polarity. Well, that's not really our understanding of the view of the Earth. And by understanding the magnetic field, we'll get a little bit of an idea of what happens next. See, when you look at this model, one of the things that stands out is that the north magnetic pole and the magnetic north pole are not lined up with one another. The geographic north pole is the pole of rotation of the planet. The magnetic north pole is the pole for the northern portion of the magnetic field of the Earth. And not only are they not lined up, and the difference in angle between the two is referred to as declination, the declination changes over time. The north magnetic field is known to wander, mostly around the pole and up in the northern latitudes, but it has happened over historic time. So why? Why would it be that way? Well, if you look at the magnetic field as we can image it here, this is from Glasner and others at the University of California, Santa Cruz's Institute for Geophysics and Planetary Physics. They took their data of the magnetic field and developed a three-dimensional image of it. This is a slice through that three-dimensional image. You can see there is a north and south magnetic pole to the field, and that we have lines of interaction in the field, but you can see that it's a much more complex thing. And it is a manifestation of the complexities of the core of the Earth. The core, as we saw earlier, is metallic. It is a metallic nickel-iron alloy. The inner core, solid, rotating, spinning very fast, faster than the planet itself, surrounded by an equally fast, spinning, molten core of nickel iron. And that molten core of nickel iron is spinning. And within the spinning, there are all kinds of currents and eddies. Metallic material have electromagnetic properties. Electric fields get set up in the plane of rotation of all of these little currents and eddies, and at right angles to it is a magnetic field. The net sum of that very chaotic magnetic field piecing together is the magnetic field of the Earth, which is a weak magnetic field on the one hand, but a pervasive one all over the planet on the other. Well, how does that help us? Well, enter Keith Runcorn and some of his colleagues. He's at Cambridge and was a graduate student. Keith is developing a brand new science, paleomagnetism. When rocks that form through igneous processes, like a lava flow on the planet, they crystallize with silicate minerals. Silicate minerals make up the bulk of the rock of the planet. Whether we're looking at the crust of the Earth or we're looking at the mantle, it's silicate minerals all the time. But along with the silicate minerals are some accessory minerals. These are minerals that have some abundance but really aren't important in making up the bulk of the rock. In igneous rocks, one of those accessory minerals is magnetite. Magnetite forms long needle-like crystals in the rock that have, as the name suggests, a magnetic property. So while the rock hasn't formed yet and it's still molten, some of the first crystals to form are magnetite crystals. And because the rest of the rock is still molten, these crystals can rotate into the magnetic field of the Earth and take on the magnetic properties of that field. They become little compass needles. Well, when the rock then crystallizes and hardens around it, the compass needles are now pointing to where the North Pole was. So what Runcorn did was he went through rocks from Europe and North America and other places, and he took them back to the lab, and these samples were oriented samples. So he marked carefully the north, south, up, down directions, so then when he got to the lab, he could uniquely identify their spatial orientations and then look at where the little magnetite crystals were pointing. And if you do this from enough places, you can fix the pole at any time in the past and come up with what Runcorn referred to as a polar wandering curve. Problem he had was he didn't just come up with one polar wandering curve. He came up with numerous ones, and I can show you the problem by just looking at two of the numerous curves. Is they all showed that there was like 112 poles several hundred million years ago. Here we're just showing two of the curves, not all 112. But you notice some things. One, not only do the poles, this is showing where the North Pole was located, not only does the North Magnetic Pole differ, the closer you get to 200 million years, all of a sudden, from 200 million years onward, it gets closer and closer and closer until, in all cases, all 112, and I'm only showing you two, the curves merge, so there's only one magnetic North Pole today. Now, there's a lot of reasons in physics why there weren't 112 different north magnetic poles in the past. But he understood something. Just as Wegner had started out with the question of ice and stumbled into something else, the movement of the continents, so had Runcorn. Because he realized that there must be only one pole. So if you fix that in your mind, then you can take a look at the other aspects. The other aspects were, if the pole had one wandering curve, then the other thing that was moving were the rocks. And if you account for that movement, so you get one polar wandering curve, what happens more than 200 million years ago is you reconstruct Pangaea, just as Al Wegner had said it was. Well, there is some differences here in that Runcorn wasn't, a meteorologist. He was a geophysicist of note coming out of a famous institution. His work was overwhelming. So when Runcorn talked about his work, he said, I don't know how this works. I do not know how the continents are doing it, but they are definitely moving. He showed his geophysics, his paleomagnetic evidence, but he also showed Wegner's. And together, by then, in the 1950s, people realized that the continents had moved. They didn't understand why. Until they figured out the Armillo event. You see, paleomagnetism wasn't the only way the Earth was being studied. There was a huge study of the ocean floor. Some of it had to do with magnetism, but first let's talk about the ocean floor. The ocean floor was starting to be mapped in the 50s and 60s by technologies developed for use by the Navy involving sonar. This is sound waves penetrating the ocean column. Well, in a single beam sonar system, you could send that sound wave down to the ocean floor and receive the signal back. The depth to the ocean floor would be a function of the two-way travel time of sound through the water column. If you have enough points showing you the bathymetry, the depth, you can create maps very similar to what we do with elevation data to create topographic maps that we studied earlier in the term. By the way, today, we can use multi-beam systems to map swaths of the ocean floor and get three-dimensional renderings of that surface. But that's a discussion for another time, because in those days, you only had single beam technology, and what you were really getting was a view of the ocean floor in a transect underneath you. And these transects had to be put together and mapped. And there were a number of people who did work on these maps, but the person who was the most prolific in making these ocean floor maps was a geoscientist named Maria Tharp. Marie Tharp, who lived until 2006, is really credited for pushing our understanding of the ocean floor and ocean floor features by putting these huge maps together. Now, her and other marine geoscientists like Harry Hess had a lot to do with getting these maps of the ocean floor out and looking for interpretations. But what Tharp did was arm all of the marine geoscientists and oceanographers with a better understanding of the ocean floor. And the ocean floor was not what oceanographers thought it should be. Because at the time that these studies were being done, oceanographers thought of the ocean floor as a big pond, like a pond where you just collected mud and sediment coming off of the continents. In fact, if you drilled through that, you'd have a complete history of the planet. Not so. What the maps of Marie Tharp and others showed was that the ocean floor was just as dynamic as the surface of the continents. There were ocean ranges, mountain ranges, the mid-ocean ridge system that crisscross through the ocean basins. If you look at a transect from North America to Africa across the North Atlantic basin, you can see this, that the ocean floor is this dynamic place. If you look near the Caribbean, you'll see a deep ocean trench. There are deep ocean trenches in other places on the ocean floor, and seamounts and abyssal plains. Quite a dynamic place, and very poorly understood. In an effort to understand it, geoscientists were looking with various aspects of the ocean floor, not just mapping its topographic or bathymetric features, but doing other things. Now, some of these scientists included three men: Vine and Matthews. Vine was the graduate student, Matthews was the advisor, and they were at Cambridge. And then a Canadian scientist, Morley. What they were doing was looking at the ocean floor through the magnetism. And they're taking a magnetometer attached to a research vessel and crisscrossing the ocean basins, going over mid-ocean ridges, and they're getting a signal. The signal from the rock is showing the magnetic field, and what they found was totally bizarre. And they had no idea what they were looking at. And this is a look at the data. I want you to look at the observed profile on the bottom. I'll explain it to you. Along the line, the ship is transecting. Data is being collected. And anything that is stronger than the magnetic field of the Earth baseline is called a positive magnetic anomaly. Anything that's below that is a negative magnetic anomaly. And to sort of give you a little deeper dive into this, I want you to think about this in terms of bar magnets and a magnetometer. If I brought a magnetometer into a lecture hall and put it in front of you, I could get the base magnetic field of the planet at that location. If I were to then take a bar magnet and line it up right underneath the magnetometer with the magnetic field of the Earth, what I would create is a positive magnetic anomaly because the Earth's magnetic field would seem more intense there than the base. Well, if I turn that bar magnet in the opposite direction, so it was no longer lined up with, but was opposite the magnetic field of the Earth, I would get a negative magnetic anomaly because what I would look at in magnetic intensity would seem completely depressed. If you take all these lines across mid-ocean ridges, you can do a mapping of the ocean floor in terms of the magnetic properties. And what they got looked like tiger stripes. The mid-ocean ridge is right in the middle. And from the mid-ocean ridge out to either side, what you see are positive, negative, positive, negative, positive, negative, positive, negative anomalies. Now, that's hard to understand. And for a long time, Vine and Matthews and independently Morley had a lot of problem resolving this until they saw the work published, very recent work published, by a man named Alan Cox. Alan Cox was an incredibly brilliant man. He had a tragic life and died tragically in 1987. But part of his brilliance was he set up a lab in Menlo Park, California, at the Western Regional Headquarters of the U.S. Geological Survey. And in this lab, he was doing a combination of high-resolution radiometric dating to get really resolved age dates and high-resolution magnetic property of rock samples. So he literally has people all over the world sending him rock samples of very recent volcanic flows. Recent being from, thousands of years ago to millions of years ago, but not hundreds of millions of years ago, not to start. And what he found was shocking. When a lava flow occurs on the planet, the magnetite within the flow lock in the magnetic field of the Earth. They literally point to where the North Pole is, the South Pole is. And when Cox looked at rocks that were maybe 400,000 years old, those really young rocks, they would say that the North Magnetic Pole is in the Northern Hemisphere. And this is not earth-shattering because that's what your compass would say. But what happened was when he got older rocks that weren't too old, say 800,000 years old, every rock on the planet that was formed through an igneous process at that time, lava flows from various volcanics, they all showed that the South Magnetic Pole was in the Northern Hemisphere and the North Magnetic Pole was in the Southern Hemisphere. The polarity of the planet was reversed from what it is today. But if you go back in time 1.2 million years ago, what you would find is the polarity is exactly the same then as it is today. As if the polarity of the planet was flip-flopping relatively quickly and in short order over geologic time. So what you're looking at here is the magnetic stratigraphy of the planet for the last 5.5 million years. 5.5 million years at the bottom of this chart with 0 at the top. And all the color-coded areas show you normal polarity. That would be polarity as we see it today. And then the white areas in this graph from bottom to top are showing you areas of reverse polarity. And you can see it's flipping back and forth through time. What I've also put here is something called the Armijo event. The Armijo event is really great because it's a real standout of a positive magnetic anomaly that's very short-lived within the Monte Yuma reversed event. Markers in time are great things in geology and the earth sciences. It's because these markers in time are always something we can follow around, that we know the age of something. And I want you to look at that data again. This time what I'm going to do is I'm going to take this chart and I'm going to lay it out so that 0 is at the mid-ocean ridge axis and 5.5 million years goes off to one side. And then I'm going to take the chart and do it in the opposite direction so it goes from 0 to 5.5 million years or so in the other direction. And you'll see. So here it is. And what you notice is that the positive magnetic anomalies are lined up with the positive magnetic anomalies are lined up with the times of normal polarity on the planet. The negative anomalies are lined up at the time of reverse polarity on the planet. And one of the things that was recognized right away was the Armijo event. So what's really important here to look at is that Vine, Matthews, and Morley were able to do something with the paleomagnetic data. They came up with a model that made a lot of sense. So if you used Alan Cox's stratigraphy of the Earth, one of the things you could do is look at how it is being reflected in the seafloor. Now, the flipping in time of the magnetic field has nothing to do with the movements here. They're just being recorded during the time of the movements. As the seafloor spreads apart, new oceanic crust and lithosphere are formed through volcanic and dynamic processes right at the mid-ocean ridge. When volcanic lava flows form on the ocean floor, they lock in the magnetic field of the Earth. When seafloor spreading pulls them apart and new lava fills, that new lava is going to lock in whatever the magnetic field of the Earth is at that time. If the magnetic field of the Earth is switching back and forth in time, then the rocks are going to reflect that over time as seafloor spreading continues. This model of seafloor spreading is very helpful in understanding the biggest problem with continental drift was that continents weren't drifting at all. They were not plowing through oceanic crust. They were riding along somewhat passively with ocean plates as well moving, so that in seafloor spreading is sort of showing us that the problem we thought we had, we don't. The mechanism is quite clear here. Ocean basins are expanding, continents are moving, that the entire hard outer shell of the Earth was in motion. Now, before we go on to look at that even deeper, I do want to just take a moment to look at the science here. Vine, Matthews, and Morley predict seafloor spreading. They say this is what the evidence is. Well, you test that model, and they did in the papers that they wrote subsequent to the research. And they tested the model in 4 ways. First, they were able to correlate the magnetic stratigraphy of the Earth to the data they saw across mid-ocean ridges and rises. They were actually able to correlate across a mid-ocean ridge from one side to the other. The third test was correlating along the same mid-ocean ridge or rise. Can you correlate your data across a transect of the East Pacific Rise with some other place on the East Pacific Rise? And then finally, can you correlate your transect from any mid-ocean ridge with any other? And yes, you can. You can take the mid-ocean ridge or rise, like the East Pacific Rise, compared to the mid-Atlantic ridge, and you could correlate the data. And this was huge. And this really, really changed the game. Now, it didn't quite get us to what we think of in plate tectonics, but it got us in the right direction. We're almost there. And we could test this model of the ocean floor spreading ourselves. And one of the things we could do is test it by looking at the age of the ocean basins, because one of the things you would predict from this model is that the youngest basaltic oceanic rock should be in the mid-ocean ridges, and that the age of the rock should get progressively older as you get away from the ridges. Well, I'm showing you the ages of the ocean basins color-coded. If you look at the color code on the left, the oldest rock is blue, the youngest rock is red. The oldest rock here is from 140 to maybe 180 million years old. So the other thing we notice is that the ocean floor is relatively young, geologically speaking. It's no older than about 180 million years, and only in a few places. And if you understand that and you accept the model, then you can do something else as well. Take a look at the Atlantic Ocean basin where a big portion of the rifting that tore Pangaea apart occurred. One of the things you notice is that the bluish rock in the North Atlantic basin is not repeated in the South Atlantic. This tells us that during the rifting of Pangaea, the North Atlantic basin opened first, and then the South Atlantic basin. Of course, the model isn't quite complete yet. Seafloor spreading isn't quite yet plate tectonics. If the seafloor were spreading everywhere and the Earth just continued to grow, it would be expanding. And there were some people who thought perhaps the Earth was an expanding planet. Lots of evidence and lots of geophysics to show that it wasn't doing that, but something else. If the seafloor is expanding and the planet isn't, then the seafloor must be consumed. And this leads us to the work of people like Hugo Benioff, who are studying the deep architecture of the planet using seismic waves, and then studying the deeper parts of the crust and the upper parts of the mantle. And they found something very, very interesting. And we've already seen it ourselves, but we can go over it again. Benioff and others found that when we looked at the epicenters of earthquakes and then checked the depth of focus, that there was belts of seismicity. These belts of seismicity that ran around the planet lined up with divergent margins where we had seafloor spreading. They were also on the margins of some of the continents. But it was this curious pattern of shallow to intermediate or deeper earthquakes that really he found fascinating. And on further study, he was able to determine that what was happening at these shallow and then getting deeper earthquakes in one direction was subduction, that the oceanic lithosphere, which is about 70 kilometers thick, was being subducted down under volcanic arcs, either on the margins of continents or in island arcs out in ocean basins, and that these were areas where we commonly saw a deep sea trench. It was also areas where we had explosive volcanic eruptions and we had massive earthquakes. It isn't the massive earthquakes that Benioff really paid attention to. It was the fact that you had this descending deeper earthquakes. And what he was able to show, and we even refer to today as a Benioff zone, occasionally we'll call it a Wadati-Benioff zone, honoring also the work of Wadati, is that in three dimensions, what we're looking at when we look at this pattern of shallow getting deeper in one direction earthquakes, is that we're looking at the subduction of the lithosphere. We're literally looking at the lithosphere breaking up during the subduction process. The asthenosphere is too weak to store strain and generate earthquakes. So if you run around the planet and look at this data, as Hugo Benioff did, you are looking at subduction in real time. This was starting to be now what we think of as plate tectonics, as the hard outer shell of the Earth diverging in some places, being consumed in convergence of oceanic lithosphere through the process of subduction in other places. The model filled out from there, and it came down to tracking the movement of the plates. Once they understood the plates, these rigid pieces of lithosphere are moving with respect to each other because of some kind of heat flow in the mantle of the Earth through the asthenosphere, tracking them became important. And they found that there were footprints. One of those people who did the early work was a Canadian scientist, J. Tuza Wilson. One of the footprints he found had to do with what seemingly was a problem. See, the problem early on in this emerging plate tectonic model was you could explain earthquakes and volcanism around parts of the planet, but there were places where you couldn't explain it. Especially volcanism was hard to explain in places like Hawaii. Hawaii sits in the middle of the Pacific Plate, with the ring of fire around it, with subduction zones mostly around it, plate margins all the way around it. It is in the middle of the plate, and it has some of the most active volcanism on the planet. Now, according to the islanders and their folklore and legend, the islands of Hawaii were created by the goddess Pele, who raised them through volcanic processes from the ocean floor. And she started in Kauai and Niue, and then moved to the southeast, progressively raising finally Oahu and then Maui and then the big island of Hawaii itself. And she lives, according to legend, in Halemaumau crater on the active volcano Kilauea. Now, scientists, and J. Tuzo Wilson among them, didn't describe what they found in Hawaii to the goddess Pele, who's the goddess of fire and volcanism. Rather, they ascribed it to something else. See, the legend is absolutely correct about when these islands formed. Kauai first, and then later Oahu and Molokai and Maui, and then finally the Big Island. And if you look at radiometric dates, it confirms it. The radiometric dates of the Hawaiian Islands become progressively older to the northwest and are young to the southeast, with brand new rocks forming on a daily basis on the Big Island of Hawaii on Kilauea, an active volcano. Imaging through seismic waves beneath the lithosphere shows that there is a hot mantle plume of material that is emanating from the core mantle interface, rising through the mesosphere, through the asthenosphere, impinging on the lithosphere, partially melting the asthenosphere, which in turn creates magma that burns a hole through the lithosphere and pours out in the form of basalt flows on the ocean floors. Over time, volcanic islands form. But as we see, the Pacific plate is moving over this mantle plume. So what Wilson explained is what he referred to as hotspot tracks, is that you have these hotspots in the Earth where we have these high flow mantle plumes coming from the core mantle interface that are burning holes and leaving a track on the surface. And as the volcanic island gets moved off of the hotspot, it becomes volcanically inactive and starts to be destroyed by weathering and erosion and constant beating of waves and storms, but new islands form right over the hotspot. If you look at a map of the Pacific Ocean basin, you'll see that the Hawaiian Islands are part of a chain. And that chain extends out past Midway Island. By the way, Midway Island is 27 million years old. And then there's a bend into the Emperor Seamount chain, where we have long-lost islands that have since eroded below sea level, to places like Suiko. Suiko is 65 million years old. So these hotspots leave tracks, footprints, if you will, that show the plate motion independently. And J. Tuzo Wilson was able to look at hotspots all over the world. And these hotspot tracks confirmed plate motions. In fact, you can use a hotspot track to not only confirm the plate motion, but actually know the rate of the plate movement. Remember that rate is distance over time. And if you take the average age of the rocks in Kauai, it suggests that about 4.5 million years ago, Kauai was sitting right where the hotspot is today. That's 585 kilometers away. If you take 585 kilometers and divide it by 4.5 millennia, which means million years, what you get is 130 kilometers per million years. So you can start to reconstruct the movements, and what was important here was the movements independently confirmed the plate tectonic motion and model. Now, Wilson was important in other ways too in plate tectonics, because one of the things that's important to understand is there's one plate boundary we still need to think about. It's a transform boundary, which is pretty important to us because we live inside one. But one of the things that through geometric analysis J. Tuzo Wilson was able to add to the story was he was able to confirm that motion had to transform between boundaries along transform margins that allowed for slip parallel between two plates. Now, once we put this piece to the rest of the puzzle, we have the plate tectonic model, the way you and I would think about it today, and the way we read about it in the textbook. Now, one other interesting thing has to be Harry Hess. See, before all of this was put together, during the early 60s, Harry started to look at geologic processes of the ocean floor. Harry was a rear admiral in the Navy and the Naval Reserve during World War II. He helped to develop systems for sonar and later was involved in mapping the floor and looking at geologic processes of the ocean floor. And he noticed that on the ocean floor you had deep sea trenches, you had volcanic arcs, you had mid-ocean ridges that had volcanic activity. He started to piece things together and was familiar with continental drift and the work of Runcorn and others, and he came up with an audacious model. And he himself told everyone it's speculative, and he gave a talk in 1960s, I believe it was 1968, Ocean Sciences Conference in Boston, held by the American Geophysical Union, and the place was packed. Harry's a really bright guy. He's a professor of marine geoscience at the time at Cornell University. And he proceeded in that 15-minute talk at that scientific meeting to explain plate tectonics just the way your textbook does. In fact, he coined the terms that we still use today: divergent, convergent margins, subduction zones, spreading centers. A lot of people talk about Harry Hess as the father of plate tectonics. We also don't credit him with the discovery of plate tectonics because he himself would tell you he had absolutely no evidence for it. It was just very speculative, but it would make sense of all the geologic processes and features he was seeing on the seafloor. Now, if Harry Hess was the father of plate tectonics, then Tanya Atwater was certainly the mother of plate tectonics. Now, I had the privilege of knowing and working with Tanya many, many years after most of her work on plate tectonics, in that she still works in geoscience education projects, and we've used them for undergraduate geoscience. But in the early 70s, when the model of plate tectonics was new, what Tanya Atwater did, first as a young graduate student at Scripps Institute at UC San Diego, and then later as assistant professor and researcher at UC Santa Barbara, what she did was she understood something. Those magnetic lineations of the ocean floor are markers in time and are related to the ridge axis. And here I'm showing you a map off the coast of the Pacific Northwest, showing you the markers with time. And then on the right, what I'm showing you is some of the early work of Vine. This comes from a couple of transects of Vine, several across the Juan de Fuca Ridge, which you can see on the map. And then we're comparing it to the East Pacific Rise, which would be farther south off the coast of South America. And what we can do is we take a look at the raw data I have here, and then at the bottom it's been converted to your lineation pattern that you would normally see, and then I've blown up the lineation pattern so you can see a comparison of the Juan de Fuca Ridge with the East Pacific Rise. See, what Atwater was able to express, and others picked up on later, is if you have time markers and you know where they were at a particular time in the past, then you can start contracting plate motions. You can start reconstructing plate boundaries in ancient times, or you could project them forward. To project them forward, you would have to look at current motions or rates. We talked about rates earlier, right? Rate is equal to distance over time. We could do that with the data that we see here. If we take a look at Vine's data for the Juan de Fuca Ridge, there is a marker that I show here at 2.5 milliana or million years. That's 90 kilometers away from the ridge axis. if we're looking at rate, then the half spreading rate would equal 90 kilometers divided by 2.5 milliana or million years would equal 36 kilometers per million years. Now, this is not rocket science, and it's really all the math you need for the course, right? That shows us movement over time. But when we look at modern movements, we always convert that to millimeters per year. When I ask students to do this sometimes, their head spins. And so what I want to do is show you a quick math hack on how you can go from kilometers per milliana or million years to millimeters per year. So it starts by writing the 36 kilometers per milliana in sort of a mathematical form, 36 kilometers over 1 milliana. And by the way, what I'm showing you here, don't take notes. Just kind of follow along. And then when we get to the end, you'll realize that this is a really good math hack that you can use. So the first thing we want to do is convert 1 milliana, to it's millions of years, to millions of years. So the way we do that is multiply this by the conversion factor. 1 milliana equals 1 million years, and you get rid of milliana. Now you've got this in kilometers per years, and that's not really what you're looking for because you want to convert kilometers now to millimeters. The beautiful thing about the Standard International Unit system is that kilo in kilometers means 1,000. And then milli in meters means 1,000th. So we could easily convert kilometers to millimeters. We're going to do it in 2 steps because it makes kind of sense. First, we'll convert kilometers to meters. There are 1,000 meters in 1 kilometer. Kilo means 1,000. Get rid of the kilometers. Now, we're not done yet because we want to get meters down to millimeters. There's 1,000th of a millimeter in each meter. There's 1,000 millimeters per meter, so we've got now millimeters per year. Now it's just a matter of doing the math, right? But you've got 1,000 times 1,000 over a million. 1,000 times 1,000 is a million. A million divided by a million is 1. So what you come down with is 36 millimeters per year, and that's the math hack. If you see something is 36 kilometers per milliana or a million years, then you know it's the same as saying 36 millimeters per year. And by the way, if we do all this for the East Pacific rise, what we see is that the East Pacific rise is moving faster. The half spreading rate of the East Pacific rise is 52 millimeters per year. Now I am using half spreading rates. Why is that? Because I'm only going from the spreading center in one direction. The full spreading rate would be considering both sides. And we like to talk in terms of the half spreading rate because that's what we're actually working with the data. Now, we're being able to project into the future because we can look at things like rates. But one of the things Atwater really did was she looked at the magnetic lineation patterns on the ocean floor and looked at modern geology and modern plate configurations. And what she was able to do with that is go backwards in time. That is, you can start reconstructing the past if you do this several times through several iterations. And that's what we're showing on the left, is taking what we know and working through models of the past. When we do this for the San Andreas transform boundary, we can get an interesting idea on how it formed. Let's take a moment to look at this. This is from the work of Tanya Atwater. It's a simple animation so that you can see it. But what we see in this animation is the plate boundary that we call the San Andreas boundary itself forming by the interaction and collision of the Farallon plate and the absorption of the Farallon Ridge, a spreading ridge. As that occurs, the San Andreas Fault grows and opens and moves northward. We can confirm today all of those motions in a real-time sense using GPS technology. That allows us to go to anywhere on the planet and locate a monument. A monument is something we affix in the ground, and with that monument, go back every year and look at its position. And we record its position, and it turns out the resolution is plus or minus 1 millimeter anywhere on the Earth. With that kind of resolution, you can now track the plate motions directly. And what we see when we look at the motion of North American plate and then into the San Andreas transform boundary is confirmation of everything we know about movement and slip along that boundary. It further confirms not only the plate tectonic model, but our understanding of the geology and the motion and slip along the San Andreas boundary and the San Andreas Fault that is a part of it. So today we got a greater understanding of the plate tectonic model, how it developed, and how it helps us understand places like the San Andreas transform boundary, which is part of our home. We will continue that study as we go on to look at volcanism and other dynamic Earth processes related to the plate tectonic model, related to the mechanical system that is the Earth.